All right, I want to make sure we had tools enough to complete the next assignment. So we're going to talk about area under a curve. I mean, this has kind of been our example along the way. This says specifically that if y equals f of x is non-negative and integrable over a closed interval from a to b, then the area under the curve from a to b is exactly the same thing as the integral of f from a to b. Okay, and it's important for this to be the non-negative thing, and we're going to take a look at that, and then the next, toward the end here, we're going to kind of look at some of these properties and how that impacts. But if we were to look at the definite integral from pi over 2 to 1 of sine x dx, I've got a couple of these pulled up, and we're going to take a look at them and see if we can understand maybe what is happening as we look at these. So I'm going to grab this Desmos doc here again, and you can see here on this particular line, I've got the definite integral from pi over 2 to 1 of sine x dx, and it says it's negative 0.54 or something. Well, as an area, that doesn't make a heck of a lot of sense, and even less so the integral from 1 to 4 of x squared minus 4x plus 3 is equal to 0. And it would seem like, 0 shouldn't be a valid answer to that. Well, let's take a look at the sine graph and see if we can figure out what's going on here. Now, whereas x equals pi over 2, and I guess it was negative pi over 2. So at negative pi over 2, that's what we've got there, and we're going to 1. Let me write x equals 1 in there. So in that gap, if we try to draw those rectangles in there, and I'll kind of zoom in on that part, if we try to imagine what's happening there, these rectangles, the heights that we're coming up with our calculations in the Riemann sums, the heights are negative. The widths of the rectangles are still positive, but if we do a positive number times a negative number, it's going to give us a negative area in there. And that's what's causing this problem here. So this negative area, actually when it is combined, and if I take a look, if I just went to 0, keep in mind that negative 0.54 there, if I go to 0 in this, I lost my pi over 2. Let me get the divided by in there. Wow, I had all kinds of issues. Okay, so that's a negative 1. That's even more, and it says that, so what happened here is from negative pi over 2 to 0, it gave me negative height, so I got negative area calculations, but then when it went from 0 to 1, if I go back here and try to get rid of all of this, the 0 to 1 part, I was getting positive heights, and that's a 0.45, so it was subtracting from this one over here. So when part of the graph is under, it's not really an area that I'm coming up with, and I need to be aware of that, and be aware of when my function is below the x-axis, because if the question is specifically about some area that's trapped in there, then I shouldn't accept negative areas. Now, most of the time, I actually am happy with it taking the negatives where it does and the positives where it does, and we'll see some examples of applications where that's actually an important thing. So what's going on in this other one, if we look at that from negative, from 1 to 4, if we go x equals 1 to see where that is, and to 4, I don't know why I'm not seeing those vertical lines. Oh, I turned them off. Okay, so x equals 1 to x equals 4, between there, what it's saying is I've got these negative areas and negative areas coming in here from the negative heights, and positive areas from here. So what I have to account for is if I want an actual area as an answer, I've got to figure out that this crosses over from 0 to 3, that's going to give me a negative. And so if I went, or from 1 to 3, sorry, if I went from 1 to 3, it says that's a negative 4/3. And I need to say, well, I'm going to make that positive if it's area that I'm considering. And then I'll do from 3 to 4. And I had the 4/3 under the 1 and another 4/3 there. So I actually have 8/3 is the total area that's trapped in there. If I'm not going to account for the negative part in there. And again, we'll have questions about both of those, so you need to understand how the question is being asked and how you need to deal with that. Okay, and that also highlights why it had to be negative, or why we only truly get the area if the function is non-negative on that closed interval. All right. So here's a property, the integral of a constant. If we think about this, this goes back to our train problem at the very beginning. If we have a function that is just a constant, if this is f of x equals c, and we go from some a value to some b value, okay, well then what we're getting is just a rectangle, and the width of that rectangle is b minus a, and the height of it is c, and so the solution, I can appeal to the geometry of what's happening here and don't have to go to my calculator and approximation. I can say, well, obviously because of the geometry of this situation, that has to be c times b minus a. Okay. Now, there's some other geometry-related situations that I could look at. If I was doing, if I had y equals the square root of 4 minus x squared, well, square root of 4 minus x squared is half a circle. And so if I was looking for that, I mean, I could go to my approximations, but I also know this is a circle of radius 2, so it's going to be 4 pi, and it's only half of the circle, so divided by 2, so this area should be exactly 2 pi, and so if I was asked to do the definite integral from negative 2 to 2 of the square root of 4 minus x squared dx, I can say that answer is 2 pi. Because of the geometry of the situation. If I have just a straight line, my straight lines are going to make triangles or trapezoids or something like that. I can see that if I had this going from A to B, well, that is just going to be a trapezoid, and if I don't remember the formula for a trapezoid, I can cut it up and make it a rectangle and a triangle and find those separate areas and add them together. So there are some of these that I should be able to come up with exact answers for without resorting to going to a calculator to help me out, just because there are some geometric formulas that I can apply. Okay. So, some other area considerations. Actually, I'd already dealt with the other area considerations. So we're going to jump ahead here to the rules for definite integrals, which is actually the first part of lesson 3, but it's a part of this assignment, so we need to get it covered. Okay. And this first one, some of these are going to look like the derivative ones that we had. So this first one especially, that says if you are doing a definite integral of something that is f of x plus g of x along the way, you can actually split that into the definite integral from a to b of f of x plus the definite integral from a to b of g of x. And it's basically because the overall height of this thing is just the sum of the heights of those two things. So if we're thinking about our Riemann rectangles that we're building here, it's like we're just stacking one on top of another. So we might have This might be the f of x plus g of x, and maybe this part of it gives us the f, and the rest of it, this part is the g, is the gap between those, where the blue line is the f plus g. And so when we build the rectangle in this area, we can either give it the full blue height, or we can give it these two heights together, regardless of how we do that. So if it is beneficial to split it up, then you absolutely can split that up. And that goes for addition or subtraction. Okay. Our second one in here, if we look carefully at what we've got, this is A, this is B, this is B, this is C. Okay. So this is saying we've got one function. Here's our function f, and we've got a point A, we've got a point B, and we've got a point C. And it says that if you were doing this definite integral, and I'm going to display these all as area things, it just makes it easier to conceptually with what's going on there, then this red part that's over here, this is the definite integral from a to b of f of x dx. And the black part over here is the definite integral. I made two b's, that second b should be a c. This is the definite integral from b to c of f of x dx. Okay. Well, if I add those two things together, pretty clearly what I'm getting would be the same thing as if I went from A all the way to C in one shot of f of x dx. Okay. So that's all this is saying here. I've got one set of Riemann rectangles that go along with the red area, and then they pick up with the black ones in the black area there, and so I'm just adding them all together to get all of the rectangle areas accounted for. Okay, hopefully that makes a lot of sense. All right, my next one, k times f of x dx. So, well, what is this k doing? This is k times f of x is just f of x with a vertical stretch. So if I vertical stretch the function, I've changed the height of every one of my rectangles by exactly the same amount. Okay, so I've made every rectangle k taller than what it was before. So my overall area should be, well, here's where I made every one k taller than what it was before. And this one over here is where the result is k times as much area that's in there. Okay, so in the Riemann rectangle language there, all of my rectangles got k times as tall as they were, and so that portion of the area calculation, that's they're not similar because we didn't stretch them in both directions the same amount, but that one vertical stretch made the overall area k times as much. Okay, I don't know if you can see this one clearly on here or not, but this is the definite integral from a to a of f of x dx, and it says that's always going to be equal to 0. Well, the idea there is that if here's our function f, if we go from a to a, then our Riemann rectangle has a width of 0, literally width of 0, and so the area can be nothing but 0. Okay, and then finally here, and then we'll wrap up this video. This is an interesting property. Okay, here's our function f, and here's our a, and we'll put b over here. And it says if you go from a to b, then you're going to get some number. Okay? But if you flip around, if you got that backwards and you went from B to A instead, so what if you started here and moved this direction instead? What if you got them mixed up along the way? Well, the effect of that, if you remember when we determined the widths of our rectangles, we said it was B minus A divided by N, right? Well, when we're doing that now, if we get those switched around, then it's going to switch to an A minus B over N, and we're going to have a small number minus a bigger number divided by N, and this is going to be negative. And so my areas are going to come out the opposite of what I expected because the widths are going to be negative. The heights are going to be what the heights are, but if the widths are negative, when I do the multiplication of a positive height times a negative width, then I'm going to get a negative answer. And so when I switch the limits on my integrals, I get exactly the opposite of an answer of what I had when I started. Okay. This, like I said, gets us a little bit into chapter 3 or lesson 3, but it does, some of those problems will show up on the next WAMAP. So I want to make sure it was on there for you.